The third concept we're going to look at from combinatorics is combinations. And this is a truly useful concept. It comes up a lot in questions, and sometimes not even when you're not really thinking it's a accounting or combinatorics question. So let's just start with an example so you get the idea. Let's say from 8 people working in an office, 3 are chosen to form a committee. How many different committees are there? So if you started this the same way we started the permutations question, you may say, well, there's 8 ways to choose that first person on the committee. There's then 7 people left to choose the second person, and 6 people left to choose the third person. And you could multiply those, and what you'd have is 8p3. That would be a permutation. The difference between that sort of question and this is that in a combination question, order doesn't matter. All we're interested in is the composition of the committee. Who's on the committee? Which 3 people are on the committee? Not who was chosen first, second, or third. And if you just did the list of permutations, you'd end up with a lot of replication. In fact, let's say we just wanted to look at the committees that have A, B, and C on them, the persons with initials A, B, and C. We'd have 6 different committees, and I've listed them all down here in the lower left-hand corner. A, B, C, A, C, B, etc. 6 different committees, all with the same 3 people on them. And so, in essence, we would have counted 6 times too many committees. And so, the calculation needs to take that into account and divide by 6. And so you can see here the 6's cancel out, and you end up with a much smaller number. In this case, 8 times 7, which is 56. So in the red box on the right is the formal definition for combinations. I really wouldn't worry about that too much. You can see that it's just permutations divided by r factorial. R factorial is the number of ways of ordering r objects. In our case, we had 3 objects, 3 people on the committee. The number of ways of ordering 3 people is 6. So really all you have to do is just start writing out n factorial, only write out r numbers, and then divide the whole thing by r factorial. So I'll give you an example. 7 choose 4. This could be, for instance, a student with 7 textbooks, and he or she is going to pull 4 of them out to put in a school bag. How many ways are there to do that? Well, 7 choose 4. You start writing 7 factorial. 7 times 6 times 5 times 4, and you stop when you've written 4 numbers. And then you divide this by 4 factorial. 4 times 3 times 2 times 1. Now notice there's the 4's cancel out, and then we've got a 6 on the top and 3 times 2 on the bottom, and the 1 we can essentially ignore, and you end up with 7 times 5, which is 35. So there's 35 different ways the student can choose 4 books out of 7 to put in a school bag. Well, what if we look at a slightly different problem? How about choosing 3 books from the 7? Well, again, you start writing 7 factorial, you stop when you've written 3 numbers of 7 factorial, and you divide it by 3 factorial, which is 3 times 2 times 1. Well, again, we've got the 6 on top and the 3 times 2 on the bottom. They cancel out, leaving us with the same number, 35. Is that a coincidence? No, it's not a coincidence, because if you think about it, taking 4 from 7 is really the same as leaving 3 behind. We should have the same number of possibilities for how many ways are there to leave 3 books on the shelf as to take 4 books from the shelf, if there are 7 books in total. And so this is actually a really nice shortcut if you're working these out pencil and paper. Always try to make the r as small as possible. It also illustrates there's a nice symmetry with combinations, and I'll show you a little bit more of that symmetry in a second. Let's go to one example that yields a much bigger number. 49C6. So what is this? Well, this turns out to be the number of lottery tickets that are possible to buy for Lotto 649. In Lotto 649, if you're not familiar with it, you choose 6 numbers from 49, and the order doesn't matter. So if you wanted to buy every single combination, it would be 49 choose 6, which is 49 times 48 times 47 times 46 times 45 times 44. I've stopped when I've got the first 6 numbers of 49 factorial, divided by 6 times 5 times 4 times 3 times 2 times 1. Now, this isn't something you'd want to do in your head. The number turns out to be 13,983,816. Let's take a look at the symmetry. If we are thinking of choosing 0 objects from a set, how many ways are there? Well, there's really only one way to choose 0 objects, and so n choose 0, regardless of what n is always 1. So for instance, 8 choose 0 would just be 1. Choosing 1 object out of a set of n objects, well, how many ways are there to do that? There's n ways. So for instance, 8 choose 1. You're choosing one thing out of 8. There's obviously 8 ways to do that. Let's go to the other end. If you're choosing n minus 1 objects from n objects, for instance, choosing 7 objects out of 8, you can do that 8 ways. Again, it's just like choosing 1 object to be left behind. If you have 8 objects and you're choosing all 8, there's only one way to do that. So there's a nice symmetry in the combination calculations.